Okay, good afternoon. Welcome back. We have a variety of technical presentations in this next section. And the first one was submitted, recorded from Weonjung Sohn, and it's called Compact and High Performance Activated Carbon Incorporated Membrane Bioreactor with the addition of biofilm carriers. Weonjung Sohn is currently a PhD student at University of Technology, Sydney, under Professor Hoyoung Sun's supervision. Her main research interests include biological nitrification process in membrane bioreactors and reverse osmosis technology for nutrient recovery in a circular economy.
Hi everyone, I'm Weonjung from University of Technology, Sydney. And today I'm going to talk about my research topic, which is compact and high performance activated carbon incorporated membrane bioreactor with the addition of biofilm carriers. I'm going to talk about my research background and objectives and materials and methods and research results and discussion and conclusion. Sorry. Although many previous studies showed many different technologies to convert urine into a safe fertilizer, I believe that the nitrification of urine in a membrane bioreactor can be a promising technology to effectively stabilize urine. Firstly, since the membrane bioreactor, so-called MBR, is a technology that combines the conventional activated sludge and membrane filtration, it has better effluent quality and smaller footprint compared to the conventional activated sludge system. In addition, the membrane process enables the separation of solid retention time and hydraulic retention time in the reactor, so it has a high operational flexibility. Due to the longer solid retention time than the conventional system, it produces minimal sludge as well. Most importantly, when urine is applied as a feed to MBR, the nitrification allows theoretically maximum 50% of ammonium conversion into nitrate, and this can lead to the pH level drop to 6.2 without any chemical addition. In addition, smelly organics can be degraded by heterotrophic bacteria in activated sludge. And finally, nitrogen, phosphorus, and potassium can be recovered in one final product as a liquid fertilizer. So in our building at UTS, there is a network of pipes that separates urine from waterless male urinals. So thanks to this network, the collection of source-separated urine is possible. Therefore, both lab scale and pilot scale MBRs have been studied for urine nitrification. However, one of the main remaining challenges is long hydraulic retention time, which was reported to be 10 to 20 days in the previous studies. Considering the amount of urine production per day in a building scale MBR, the high HRT is disadvantageous, resulting in a large footprint as well as high cost and energy. Therefore, the addition of biofilm carriers can be an excellent option to resolve this challenge by supporting more biomass, leading to HRT reduction and small footprint. Therefore, I have three research objectives. First one is to investigate the effects of biofilm carriers and PAC addition on the overall performance of MBR treating source-separated urine in comparison to the conventional MBR. Secondly, to explore the effects of biofilm carrier support in MBR during the startup period in regard to the resilience from nitrite accumulation event and startup time. Last objectives is to investigate the effect of the integration of biofilm carriers and PAC on the performance improvement in terms of the nitrification rate and hydraulic retention time. So this figure is illustrating the schematic diagram of experimental setup of MBR with biofilm carriers and PAC. And the conventional MBR has the same experimental setup, only without the additives. And source-separated urine was dosed using the pH-based dosage strategy for both reactors. maintaining the pH level to 6.2. An ultrafiltration membrane module was operated at low flux, and another module connected to water level sensor could maintain the water level. It is important to choose a suitable type of biofilm carriers because the properties are closely related to the efficiency of the reactor as well as the maintenance energy and cost. In this study, round and paraboloid-shaped polyethylene biochips were chosen, considering its high surface area and light weight. And the biofilm carriers were added to one of the MBRs with 5 volume% of filling ratio to support the growth of microorganisms. Compared to the conventional hollow body type carriers, which can normally cause biomass clogging and accumulation, these flat disc-shaped carriers with low diffusion depth can have better transfer of both nutrients and oxygen, leading to the increase of specific biofilm activity, minimizing the anoxic zone of inner biofilm layer. Also, its paraboloid shape can effectively remove the excessive biofilm deposition and remaining the thin effective biofilm layer. So the two MBRs were operated in parallel. Biofilm carriers were added from the first day in one reactor, and 2 grams per liter of PAC was added after the startup time, and when the undiluted urine was fed. During the startup time, both reactors were started to be fed with 10 times diluted urine for the acclimation of activated sludge, and the dilution rate gradually decreased. When the feed ammonium concentration was over 3 grams per liter, the nitrite started to accumulate in both reactors. However, the biofilm carrier addition could shorten the recovery time by 25.9% from the nitrite accumulation event, and also decrease the startup time by 18.4%. In the second phase, when undiluted urine was fed and the PAC was added, the nitrification rate was significantly higher by 36.3% than the conventional MBR. As a result, the HRT was able to decrease to around 6 days compared to 10 days of HRT in the conventional one. The growth of suspended biomass in terms of MLSS and MLVSS, both reactors showed gradual increase, but the growth was significant after PAC addition. And in terms of the attached biomass, so 2.82 grams could make the carrier saturated with biomass and then rotate the whole reactor. And this attached biomass had very slight increase after the PAC addition, but remained nearly the same during the second phase due to their effective paraboloid shape, which could remove the excess biomass deposition by shear forces. In regards to the total organic carbon removal, the PAC addition largely increased the TOC removal rate by 10% compared to the startup time in the MBR with biofilm carriers. And this was almost 12% higher rate than in the conventional MBR. And this is because of the high adsorption capacity of PAC and the subsequent biodegradation by the formation of biological activated carbon. So finally, this table shows the composition of nitrified urine from each reactors. And valuable nutrients such as phosphorus and potassium were well remained in the permeate, indicating the potential production of 6 to 1 to 1.5 MPK liquid fertilizer. So in conclusion, biofilm carriers addition showed better resilience and shortened the startup time. And the combination of biofilm carriers and PAC significantly improved nitrification, thereby reduced HRT, and also improved the organics removal. and therefore the production of NPK liquid fertilizer in a more compact and higher performance NBR was feasible in this study. So finally, I'd like to thank the ARC Industry Hub on Nutrients in a Circular Economy. And thank you for your listening.
Thank you very much. That was an extremely interesting look into optimization of the nitrification process and incorporating various elements together that I've not seen before. Thanks for sharing that with us. So next up is Kindle Williams, who will be presenting Scaling Up an Electrochemical Nitrogen Recovery Process from Lab Benchtop to Pilot Wastewater Plant. Oh, and let me say, oh, sorry. Thank you, Sandeep, for that very interesting and innovative presentation. I look forward to looking through that with more detail and probably asking you some questions. Thanks very much for bringing that to us all. So back to Kindle Williams with Scaling Up the Electrochemical Nitrogen Recovery Process. Kindle Williams is a postdoctoral scholar at Stanford University, working with Professor William Tarpey on separations and reactions of inorganic nitrogen species in wastewaters, with a particular focus on imminent scale-up and deployment. She received her BS in chemical engineering from University of Alabama and her MSCEP and PhD in chemical engineering at MIT, where she studied electrocatalysis with Professor Karthish Manthiram. She is excited about taking actions large and small to help solve the climate crisis ASAP. So with that introduction, please take it away, Kindle.
Awesome. Thank you so much for the introduction. Can you guys hear me all right?
Loud and clear.
Awesome. Sweet. So yeah, I'm Kindle Williams. I'm a postdoc in the Tarpey lab at Stanford. And today I just kind of want to give you guys an overview of a project that we recently started based on some funding from the Stanford Dorr School of Sustainability, which started up only about a couple months ago, where we're taking this electrochemical nitrogen recovery process that we've developed in the lab and moving it all the way from the lab bench scale to a pilot wastewater plant. So to start off, just a sort of overview of what the Tarpey lab does. You got a little bit of this from Anna's presentation earlier, but we focus broadly on the development of selective materials, selective electrochemical processes to recover resources from wastewaters. And we're also interested in sort of engaging with communities to translate these technologies and evaluate their impacts at scale. So this is sort of where my project comes in, pulling in the echem side of things. We look specifically at electrochemical stripping. So you guys have seen this process a couple of times now, but I'll just walk you through the technology one more time. So essentially what we do is we take hydrolyzed urine, so urine that already contains ammonia or ammonium. This enters our reactor and we are running some electrochemical reaction, usually water splitting, to produce a pH swing. So when the urine comes in, it comes into the anode chamber, which is acidic. So all of the ammonia is in protonated form. And to sort of complete the circuit for this reaction, this ammonium is going to move across a cation exchange membrane, where it finds itself in this basic environment that's created by the reductive portion of the water splitting reaction, then causes it to deprotonate into ammonia, which is a gas. So once we have that gas, we can then push it through this gas permeable membrane and then recover ammonium as some sort of salt using an acid trap. So this can produce fertilizer in the form of ammonium sulfate, ammonium nitrate, based on the type of acid that you use. Or we could also think about using processes here to recover the ammonia that don't involve acidifying. So that's an overview of electrochemical stripping, and we've demonstrated promising performance in the lab thus far. I think Anna already showed the fact that this process works for real urine. It also works for other nitrogen-rich wastewater streams, and we can remove nitrogen content from a urine similar influent, I think this is on real urine, the data they're showing here, on the order of 12 hours at the scale that we're operating at. And recovery of all of that ammonia comes into the track within about a full day. At the lab scale, but kind of to the point of I think what we mentioned a little bit yesterday is that one of the problems we really need to solve in nitrogen valorization, urine valorization in general, is translating to the real world at scale. So some technical problems that we're working on in the lab are scale up, looking at robustness and long-term operation of electrochemical stripping. And also we have a project going on as well to sort of help with self-sufficiency of this process through integration of the eChem with solar power. And of course, in parallel with all of this, we want to be engaging with stakeholders and seeing how this technology could be useful to people and how it will impact people if we do deploy it. So I want to focus specifically on the scale-up aspect of things today, because we are, this is sort of my project. We are funded, like I mentioned, by the Stanford Door School, and specifically their sustainability accelerator, which is looking at taking technologies that exist in the university and translating them to real world use as soon as possible. And we actually have some great facilities that you guys might have seen in our tour video in the Codiga Resource Recovery Center, which is a pilot scale wastewater treatment plant on campus. It services the Stanford dorms and gets about 30,000 liters per day of wastewater. The nitrogen content in that wastewater is equivalent to about 1,000 people per day. So you can imagine there are more than 1,000 people living in the dorms, but they're not doing all of their waste production in the dorms. So that's about what we receive. And this is a use case that allows us to test the limits of our technology, which actually works better in these more concentrated urine streams than it does in dilute wastewater due to the lower conductivity of the wastewater. So we're hoping to sort of test the harder use case and then apply some of the learning that we get for reactor design to direct application to urine as well. So this involves a volume-wise scale up of about 3,000 times, which maybe you guys are sort of on the engineering side of things, you know, it's not a trivial scale up. You really need to know how your process works in order to achieve a 3,000 times scale up directly. So that's one of the first things we're trying to do in our approach, is to fill out some knowledge gaps in sort of the mechanisms of how the transport of these nitrogen species work in our system. So isolating transport of the ammonia gas across our gas permeable membrane and studying, so basically establishing like a rate law for that process. Varying a bunch of parameters such as electrical current in the system, catholyte, salt, identity, and concentration, as well as varying their relative chamber volumes, to all sort of help us paint a picture of what's going on in this reactor better than what we already know. And this is all with the goal in mind of producing a process model that will help us to from a physics standpoint, understand what's happening and also predict how we might best achieve scale up through different reactor designs. So we've been working on taking this from sort of a parallel plate configuration that we've shown in all of the images that you've seen thus far to something more like this, where you have an annular flow reactor and sort of concentric rings of processes happening. And we'll also, such a process model will help us understand, you know, what are the impacts of if we try to make alternate products from ammonium salts, as well as could we possibly integrate hydrogen collection, since that is a co-product of this reaction that we're running here. So that is the scale up side of it. And then in parallel, we have other translation studies that are running Anna, who presented earlier, is working now on long-term electrochemical stripping, sort of studying the system performance over many months and identifying potential failure modes of the system. So looking specifically at membrane and electrode fouling. And then recently, a second-year PhD student in our group, Arisa, demonstrated for the first time solar operation of ECS. So this is electrochemical stripping and fertilizer production that doesn't need to be plugged into the grid. This is running entirely based off of a solar panel that she has on this little cart here. So this can allow eventually for deployment of the system in electricity constrained settings. So that's just a sort of an overview of the current focuses that we have. There's no actual results to show today, but I would love to connect with folks who are interested in learning more about what we're doing or potentially partnering with us. And just big shout out to the TARPE Lab and the Stanford Doerr School of Sustainability for our funding.
Wonderful. Thank you, Kendall, for that introduction to your ongoing research and an invitation to collaboration. I hope everyone heard that. It sounds like exciting work to be undertaking and to be involved with. Our next presentation comes from Courtney, who will be presenting a hybrid nanofiltration and reverse osmosis process for urine treatment, effect on urea recovery and purity. Courtney is a PhD candidate at the University of Cape Town, supervised by Associate Professor Dylan Randall. Her research focuses on using pressure-driven membrane separation process to concentrate urine to produce a concentrated liquid fertilizer. Her research group's core focus is to valorize urine through resource recovery. And if you're there and can share your screen.
Hi there.
You there, Caitlin?
Yes.
Okay.
Can you hear me?
Oh, good. Yes, we hear two folks. Oh, I see. Your name on Zoom is different.
Oh, sorry about that.
No problem.
Different computer.
Okay, good. But you've got screen share going, so it looks like you are ready to roll.
Slideshow. Okay, all good.
Looks great.
Great. So as mentioned, my name's Caitlin from the University of Cape Town, and basically this research is about developing a hybrid nanofiltration reverse osmosis process to create a purer concentrated urea product. And it is based on the following paper that's been published this year, I believe. So it's been mentioned a lot that urine contains valuable resources and should be seen as a resource rather than a waste. And one of those compounds we're particularly interested in was urea. When fresh, the majority of the nitrogen in urine is in the form of urea, and it has many valuable uses as a fertilizer. It can be used in cosmetics, and it can be also used as diesel engine fluid. But urine doesn't just contain urea. There are other things like organics and salts. And so that means in terms of purity, the urea only accounts for about 34 to 39% of the dissolved solids, depending on the composition. And something that's come up a lot today is salts and their effect on the fertilizers in value and pharmaceuticals and the potential for crops to uptake those. So that was something we wanted to look into. Also, because the urea is not in a pure form, it might not be as valuable to be used in cosmetics or diesel engine fluid. So we wanted to look at a way that we could purify it. So we've also heard a lot about different pharmaceutical removal methods today. Two that I'll mention in the study: advanced oxidation processes and granular activated carbon. So advanced oxidation processes have been shown to be really promising, but they don't degrade they don't physically remove the pharmaceuticals, they only degrade them. And so something that's come up a lot with the electrochemical processes is like disinfection byproducts. So that's something to think about. And then with granular activated carbon, excellent, but it also absorbs urea. So in our study, because we're focusing on stabilized or fresh urine, granular activated carbon didn't work great for us. So we previous research by Pronk and Associates showed that nanofiltration might be an alternative pharmaceutical removal method. The theory is that urea, being a small uncharged molecule, would pass through the membrane, while pharmaceuticals, which are typically larger molecules, would be rejected and concentrated in the brine. And one additional benefit is that some of the undesirable salts would also be rejected by the membrane, creating a purer urea permeate stream. The challenge with some of these studies is there's not a lot of information about recovery rates and purities, long-term operation, and the urea permeate stream is also still going to be dilute, so it would require further concentration. Just a bit of background on nanofiltration membranes. They're typically labeled as either loose or tight. So both have good rejection of divalent ions, but tight nanofiltration membranes have an improved rejection of monovalent ions as well. They kind of act sort of like an RO membrane, but this potentially comes at the cost of urea rejection. So more urea would be recovered in the brine and not in the permeate. So we wanted to look at both of those types of membranes. We looked at 6 different pharmaceuticals of varying molecular weights. 3 were considered acidic and 3 basic. We used both real and synthetic urine. The urine was stabilized with calcium hydroxide and then treated with an air bubbling technique to remove excess calcium and prevent membrane scaling. Then we used a lab scale cross-flow membrane setup where the brine stream is continuously recycled to the feed tank until the desired volume of permeate has been recovered. And then we took that permeate stream and further concentrated it using an RO membrane in the same manner, so in a batch setup. Okay, our findings. So in terms of pharmaceutical rejection, we saw that the tight nanofiltration membrane had excellent pharmaceutical rejection, above 98% in all cases. For the loose nanofiltration membrane, rejection varied, but was still good and above 73% in all cases. So that was really promising in terms of pharmaceutical removal. When we look at urea rejection, we see very low rejection for the loose nanofiltration membrane, and there was no difference between the synthetic and the real urine. So what does this look like in terms of recovery? So at a volume reduction factor of 5, which means you've got 80% of your volume recovered as permeate, we recovered 78% of the urea. For the tight nanofiltration membrane, the rejection varied for real and synthetic urine. And so this resulted in a difference in recovery. So the tight nanofiltration membrane for real urine actually rejected more of the urea. And so we had a lower recovery in the brine. It was 57% for synthetic urine and 48% for real urine. Both membranes provided quite a high rejection of organics, but you can see for the loose nanofiltration membrane, there was quite a high permeate conductivity, and this is because of that lower rejection of monovalent ions. So what does this look like in terms of purity? If we had used just RO alone to concentrate the urine, you see that the dissolved solids composition remains unchanged. For the loose nanofiltration membrane, the purity of the urea was 56%. We were able to remove 78%, 78% of the organics and only 44% of the dissolved ions. One of our concluding remarks was that we actually proposed that an ion exchange pretreatment step could be beneficial if you replaced all of the chloride ions with sulfate ions, which we had a much better rejection of. You could, in theory, improve the purity of that product with a higher urea recovery. So for the tight NF membrane, we had a really high purity, 85%. We removed 78% of the ions, 78% of the ions and 90% of the organics. As I mentioned previously, the urea recovered in the permeate is still dilute. So we further concentrated the permeate from the tight nanofiltration membrane using reverse osmosis for both the synthetic and the real urine. And interestingly, we saw no difference in the urea rejection this time. So that kind of leans into the hypothesis that the organics present in the urine may be forming a matrix that help reject the urea better. In terms of overall urea recovery, at a overall water removal from the 2 steps of 80%, you would only recover 32.8% of the urea. So just a summary of the different recoveries and removals of different treatment options. In general, you can see that the removal of salts and pharmaceuticals comes at the cost of the nutrient recovery. So we use these results to help develop a decision tree that could be used by practitioners to determine an appropriate treatment method. And you would ask a series of questions, starting with, will the product be used as a fertilizer? If yes, would it be used for edible crops? If no, you could use an RO only process. If the answer was yes, you would need to consider if the crop is salt tolerant or the soil conditions. If it is salt tolerant, you could use just a loose NF-RO combination. If not, you would have to use a tight NF-RO. Then going back to the first question, if the product is not being used as a fertilizer, does it require urea to be in a purer form, say for cosmetics or diesel engine fluid? If the answer is no, again, RO only would be suitable. If yes, you would use a tight NF-RO combination. So in conclusion, we saw that nanofiltration pretreatment was a way that could be used to remove pharmaceuticals and salts. We advised that additional ion exchange pretreatment would be valuable for improving salt removal for the loose NF membrane. Further concentration of the permeate was still required. We used reverse osmosis to do this. However, other concentration methods such as evaporation or freeze concentration could also be used. And ultimately, the choice of treatment process will depend on the quality and composition of the desired end product. Thank you so much.
Terrific. Thank you so much for that presentation. We've really run the gamut here in methods of
Yes.
Of separating different constituents and ways of doing it. So thanks for bringing that also unique take on using multiple types of membranes for different purposes to achieve different goals. From that, we're going to shift gears substantially and head from physics and chemistry to biology. We have Jeff Meilander presenting bacterial succession in human fecal waste composting. And Jeff Meilander is a biology PhD student in Dr. Greg Caporaso's lab, currently studying the microbiomes of human fecal composting. Previously, he taught students from kindergarten through graduate school in environmental science, biology, anatomy, and science pedagogy. In 2011, he volunteered on farms in Europe and South America through the WOOF organization, which inspired him to start his own nonprofit sustainability education farm called the Flagstaff Eco Ranch. The educational programming conducted at the farm engaged over 1,000 students and community members who have helped donate over 4,000 pounds of produce to underserved families. Jeff, are you able to share your screen at this point? Yes, you are. Okay.
Yes. Hi, everybody.
Go ahead.
Let me hit that presentation. All right, yeah, thanks. My name is Jeff Meilander. I'm a second year PhD student here with the Caporaso lab. And I will be presenting some preliminary data from the past year of my research. And so for me, I've always rooted for the underdog, which is why my research is focused on number 2. And in this case, especially with this bucket of presenters, the castaway of the urine diversion process here. So the goal of my research is to learn what's happening to the fecal microbiome, or the collection of genomes from all of our samples during mesophilic composting from self-contained composting toilets, and to look and see if the microbiome looks less like feces and looks more like soil microbiome in order to better understand the composting process. So for this project, I recruited individuals with a wide range of experience using composting toilets, and they used their composting toilets for 3 weeks, at which point I showed up and transferred the material from their toilets into these modified 5-gallon buckets that you can see in the background over here. So each bucket is ventilated, and it has down here, you can see a little white cap that unscrews, and this is our access port. This allows us to pull the samples out and reduce any contamination rather than pulling off the lid. So each week we show up, we pull one bucket at a time, we roll it to aerate it and homogenize the mixture. We take a bunch of photos and we document a bunch of qualitative and quantitative data. You can see Antonio here on the left. He's taking photos through the ventilation tube. And we record temperature and moisture and pH. And then, it kind of turns into like a wine tasting where we're holding up the samples and looking at the color and giving it a little bit of a sniff. But I assure you there's no tasting going on with these samples here. So we do have 15 buckets that are being sampled weekly, and the goal is to sample these for 1 year. At this point, I have 5 buckets that are finished, and we'll finish the rest of the buckets by the end of 2022. So the data that I'm presenting on, though, today is only from bucket 1 and over the first 30 weeks of this process. Partly because we were testing our lab protocols, but also we wanted to see if anything was actually happening with this experiment and what modifications should we make. So on the right, you can see the very first sample that was taken back in October of 2021 from bucket 1. And in the bottom is the most recent sample from a year later, earlier in September of this year. So not as much decomposition as I was hoping to see, but when you work with these buckets for a year, you tend to see some really good color change and decomposition. So from there, we take those samples to the lab and we extract the DNA, and then we target the V4 region of the 16S rRNA gene. And the 16S rRNA gene codes for part of a ribosome. And if you remember basic biology, ribosomes are what is producing proteins. And so in this image, you can see there's 9 variable regions labeled V1 through V9. And a variable region basically means that these regions of the gene change a lot. And we can use those changes like fingerprints to identify the microorganisms that are present in these samples. So once we add the primers, we basically take a little bit of DNA and we turn it into a lot of DNA using polymerase chain reaction. And then we run that data through a sequencer. We get lots of A's, C's, T's, and G's back, and a giant file that we can then run through QIIME2. And this is the world's leading microbiome data science platform that I'm proud to say was developed by our lab and is maintained by our lab. And so one of the cool things about QIIME2 is that it produces these really high quality visualizations. And one example here is this taxonomic bar plot. So to orient you to this bar plot, each bar in this image represents one of my samples. And each color within that bar shows the relative frequency of the respective phyla that you can see over here on the right. Now we can look at other taxonomic levels, but in this case, I'm just presenting on the phyla. You can see that my samples are organized here by bulking material in red, compost, which is changing in this image over time here in orange, our fecal samples in blue, and then our soil samples down here in green. Now, to clarify, these soil samples, I did not collect these soil samples. These are public microbiome data from the Earth Microbiome Project, and this represents diverse soils from all over the planet. And we use these as a baseline to compare my compost samples to. So if I highlight just a few of these subsamples in this taxonomic bar plot, what we can see is that the relative frequencies of the composting samples look pretty similar. And the same is true of the soil subsamples. They look pretty similar. But if we compare the two and we look at the compost samples versus the soil samples, we see that they are actually different. And in order to determine how different they are, we can create principal coordinate analysis plots that compare the similarity and the dissimilarity between each of these samples. So to orient you to this, what you're seeing right now, on the left is an image or a PCOA plot with the same data that you see on the right, but you can see down here is that it's color-coded by sample type. So my compost samples are clustering over here in orange. You can see some fecal samples up towards the top in blue, and you can see soil samples are clustering in green. The bulking material is here in red, and then in purple was a swab that I took of the inside of the toilet before we used, and the yellow is some soil nearby the toilet when it was being used. Now, to just clarify, each dot in this image represents one sample, just like we saw on the taxonomic bar plot. And the closer these dots are to each other, the more similar their bacterial diversity is. And so, for example, if we look at the fecal samples up here at the top, these samples are clustering really close together, so there's much less distance, which means they're very, very similar in their bacterial diversity. But if we pick one of these dots out and we compare it to one of these orange dots down here towards the x-axis, or maybe one of these green dots down here towards the x-axis, there's much more distance and a lot more diverse and more differences between that bacterial diversity. So we're seeing that there is some change in those composting samples, and that the composting samples are in and of themselves closer together. Now on the right side, same exact image, same data plots and samples, but it's now color-coded for time. And so the red is the very beginning of the experiment, or week 0, and the purple are the most recent samples, or week 30. And what we can tell is if we look at our fecal samples here and we look over time, we're seeing a noticeable change in that fecal microbiome, or that microbiome of those composting samples, over those first 30 weeks. And so they're becoming less similar to feces, and along this axis 2, they're becoming a little bit more similar to soil, but they are not soil yet. There's still a pretty big difference here between these dots. Now, I just wanted to quickly show you what else is really cool about QIIME 2 program with this PCOA plot, is that we can add visualizations. And if we look at these soil samples here, they look like they are all clustered really close to each other. But if we look at these in a different way, or along a different axis, we can get a better understanding of their spatial relationship to each other. And so this is really helpful when we're looking at our data points. So if we go back to that taxonomic bar plot, we can pull out specific phyla to again compare and try to understand what are the similarities and differences between these samples. And just to pick out a couple, actinobacteria, we can see are very high in abundance here in our composting samples, and not very much in our soil. And the opposite is true if we look at acidobacteria, very high abundance in our soil samples and almost nothing in our composting samples. So at this point in the experiment, we can conclude that the 30-week aerated mesophilic compost is definitely looking less like feces, a little bit more like soil, but we're not confident enough that we could call it soil yet. And so moving forward, we're seeking funding to analyze the fungal and eukaryotic organisms. as well as looking at pathogen and pharmaceutical prevalence and persistence and how these may affect the microbiome of that composting process. And we're also planning on incorporating Raspberry Pis and data sensors into some composting toilets in the future to record the data and potentially optimize the systems that are going on in the self-contained composting toilets. And we love collaborating. It's been fantastic hearing about everybody's research. And so if anybody is interested in brainstorming or collaborating with us, we're happy to have those conversations. And if you're interested in applying microbiome analysis technologies into your work, please feel free to reach out to us because we're more than happy to help out in any way that we can. And with that, I want to thank my composting team and my army of undergraduates who've helped make this happen. So thanks for that. And I'm happy to answer questions at the end of all the presentations.
Terrific. Thank you, Jeff. And then thank you for another call for collaboration. I love hearing that at the summit. And I think that's why we're all here. And it's great to see that at the front of people's minds. Also really interesting to see that that dive into applying very modern tools to a very ancient practice. Very interested to see what comes out of that as you continue with that work. This brings us to the final presentation of this section, which is Elena Bischak, who will be presenting urine storage conditions influence nitrogen absorption and plant uptake in urine-enriched biochars. So we're headed back to nutrient management and reclamation. Elena is a fourth-year PhD candidate at the Environmental System Program at UC Merced. She studies urine nutrient recovery using biochar, particularly to optimize container-based sanitation systems. So if you can share your screen, I'll let you know when I see it, and you can take it away.
All right, thanks everyone. Can you just let me know this was working because I was having issues before?
Yes, it looks perfect.
Great. Okay, well, thanks. My name is Elena. I'm a fourth-year PhD candidate at UC Merced, and I'm presenting today some work entitled Urine Storage Conditions Influence Nitrogen Absorption and Plant Uptake in Urine-Enriched Biochars. So this is collaborative work from myself and others at UC Merced, a great colleague, Saliva at UC Berkeley, and Julie at Soil. So the motivation for this work was container-based sanitation systems and urine nutrient recovery. As Chelsea mentioned yesterday, container-based sanitation or CBS systems source separate feces and urine, and Soil in Haiti currently co-composts the feces that they collect at a decentralized scale, but urine's not currently recovered. So here's a picture of one of Soil's toilets. The urine is collected in this front part here, and it goes into a container you can't see that looks like this. So I want to impress that this research was motivated by Soil's opportunity, but is in no way their current practice. So our motivation was to look at biochar as a low-tech, widely available adsorbent that's also a value-added soil amendment. So biochar is just charcoal made from different types of biomass, and it can absorb all types of nutrients, sequester soil carbon, and improve quality when it's soil applied. However, biochar feedstock pyrolysis temperature can affect the particle size, pore size, surface chemistry, among other things, all of which ultimately influences the nutrient absorption capacity. So in this study, we looked at three pretty different biochars produced at, from different feedstocks and different pyrolysis temperatures. And I was curious if these differences in the biochar properties would lead to different urine-enriched biochar nutrient quality and fertilization potential. So, however, when I was designing this study, I was thinking, okay, well, what kind of urine am I going to use? As we've covered many times throughout today, urine changes over time. When we excrete urine and it's fresh, the pH is around 6 is what I found, and the conductivity around 11. And urea is the primary solute, accounting for about 80% of that excreted nitrogen. However, when you store it in a system, bacteria is going to grow. The urease enzyme is going to catalyze this reaction at the bottom, and most of that nitrogen is going to be present as ammonia. The pH is going to rise as well as the conductivity. And then I also looked at urine in a typical like container-based sanitation style container, because I was thinking this container is open, how much ammonia is going to volatilize and how much like fertilization potential are we going to lose from that solution. So with collaborative soil, we agreed that it was about 3/4 of the way full typically and uncovered for about a day before users disposed of it. So this led to our objectives, which were to assess the effect of urine storage conditions on nitrogen absorption to different biochars, and to assess the effect of these urine-enriched biochars on tomato growth. I chose nitrogen here because of the differences in nitrogen in these different urine storage conditions, as I just outlined, because it's the most abundant plant essential nutrient in urine. It causes large environmental problems when it's left untreated, and it was also the easiest to quantify in my lab setting. So our approach was to prepare these urine-enriched biochars from 3 types of biochar in urine. We just sort of chose a ratio, soaked it for 2 days, and allowed it to drain freely over 500 micron sieve, which actually had some big impacts on the data that I'll talk about in a moment. And then we conducted a 5-week tomato greenhouse growth trial. So we used those 9 different urine-enriched biochars from the 3 biochars and 3 urine, all different combinations. We also had a urine-only treatment applied at equivalent volumes as would be present in that urine-enriched biochar, and had fertilized and unfertilized controls. Everything but the controls was tested at 4 different application rates on a dry mass basis. Plant growth indicators were measured throughout, and the dry above and below ground biomass weight and carbon and nitrogen content of that plant tissue was analyzed at the end. So getting to some results here, total biomass was variable across treatments. If you'll first look at the controls, we have synthetic fertilizer, organic fertilizer, and unfertilized control. There weren't significant differences between them. They followed the trend you might expect, with synthetic higher than organic, higher than fertilized. Then when looking at our treatments, it's kind of a wild figure, and I'm not going to put you through too much with it, but there weren't too many significant differences when looking at total biomass. Some were significantly, higher than others. For example, sewage sludge prepared with fresh urine applied at the highest application rate of 10% was significantly lower than the stored urine-only treatment applied at the same application rate. But luckily, the nitrogen data was a bit more interesting. This figure shows the absorption capacity of the smaller than 500 micron size fraction and the larger than 500 micron size fraction. QAQ is the smaller one. That's what we determined in the effluent. So after we had the sieve and let the urine-enriched biochar drain, that's what we determined to be the solid phase absorption in the part. Sorry, my dogs are in here. And then QS is what was actually used in the experiment. That's the absorption capacity of the part of the urine-enriched biochar we used, greater than 500 microns. So you can see that we lost significantly more nitrogen in the part that we didn't use. And that could be because of the higher surface area or more oxygen-containing functional groups in those small biochar particles. And it's a bit hard to, it's a bit hard to tell on this graph, but there actually is a significant difference in the larger size fraction when it was compared with prepared with fresh urine, and that could be because of the lower pH and conductivity of that urine that would lead to preferable sorption, or different sorption affinities for urea versus ammonia. So now when looking at that nitrogen data compared to the plant nitrogen uptake, we see some interesting things. This figure shows, if you'll first look at the urine-only panel, a strong positive linear relationship between the amount of nitrogen applied and the plant uptake. And that's kind of what we would expect, that urine is immediately bioavailable. We know that the forms of nitrogen present in urine are similar to those used in commercial fertilizers. But then when looking at the urine-enriched biochar, we see kind of a similar linear trend, but it's not as strong for the walnut shell. And it kind of implies some sorption and subsequent desorption of that urine adsorbed to those biochars, regardless of type. And that could be due to the pyrolysis temperature of walnut shell, around 350 C, which is good for maintaining those surface functional groups that are good for adsorption. But then when you look at these higher temperature sewage sludge and wood waste, we see some different things. There's a soil priming effect that's evident when sort of just a small amount of nitrogen was applied with the CBS and stored urine. We still see some higher plant uptake, but it's not proportional with the fresh urine. That might be due to the urea molecules being held more tightly, being held in different sized pores. It's hard to say. And you can even see here at the highest application rate of the fresh sewage sludge urine-enriched biochar, something potentially deleterious is happening with less nitrogen being taken up than was applied. And that could be due to the high ash content of the sewage sludge char. So what does this mean in a broader sense and for future work? Urine-only treatments were more bioavailable in the short term than urine-enriched biochar treatments. And that might mean that urine could be applied as a pre-plant or side dress to urine-enriched biochar to meet a crop nitrogen demand over a cropping cycle. Nitrogen adsorption to biochar was determined by the biochar size fraction and the urine type. So practically, it means it might be difficult to recover nitrogen in CBS or other urine collection systems if you're producing a urine-enriched biochar and draining it, because most of that sorbed nitrogen would remain in the effluent. But ultimately, this research shows that urine-enriched biochar is a slow-release fertilizer made from 2 neglected waste streams that can repurpose excreted derived nutrients for agriculture, both in low resource or high resource contexts. And it's led to some future questions I'm currently working on, like what is the mineralization rate of nitrogen absorbed to urine-enriched biochars, and does that fresh urine-enriched biochar nitrogen become bioavailable in the longer term? So I'd like to acknowledge some important members of my lab and also our funding sources for supporting this work. Thank you all for listening.
Great, thank you, Elena, for that. It seems like we've had quite a few different approaches to biochar and to activated charcoal, different forms of absorption by carbon in some form. So thank you for sharing that one that bears especially on direct application in the developing world, in addition to all of these more high-tech solutions that we've been looking at over the course of the morning. There have been a lot of questions asked over this period. They've almost all been answered in the chat, and that chat will be saved, and those questions and answers will be posted later on as a record. There was one outstanding question to Sudeep about the availability of that technology you're working on and what your thoughts are on when that might be something that could be available for use.
Yeah, so we've been working at the lab scale. I think we're close to where we might be able to build bigger systems. But I mean, if you're open to collaborations, if it's something that you want to evaluate for a specific pre-treatment to a process that you're working on, we'd be happy to collaborate. I think we're at the level where we can make it at a few hundreds of milliliters, but that's enough for a few liters of urine per day.
Great, thank you for that. And Elena just finished, so if there are people who have questions for her, just pop that into the chat. I'll see that as that comes up. But I guess just to wrap it up, this has been quite an inspiring session, and I'm just so impressed by how many different lines of inquiry are going forward, and how resourceful and innovative so many of them are. So hopefully with that and with this great spirit of collaboration, we will be able to continue talking and working and sharing ideas after the conference, and have even more to share next year.